For years, a specific bias has persisted in software engineering, the idea that MongoDB is a simple, schemaless document store, a tool built for rapid prototyping and early-stage startups, but not something you trust with serious scale. The reality is entirely different. Today, MongoDB powers globally distributed, high-throughput financial platforms and enterprise systems, handling millions of operations per second. High availability and horizontal scale are the predictable outputs of deterministic state machines and rigorous architectural design. We are going to construct a production-ready MongoDB architecture from first principles, starting with a single document. We will scale this single node into a globally distributed, sharded cluster to understand the exact internal mechanisms that dictate how data moves. We will dissect how the system handles microsecond query routing, multi-document ACID-compliant transactions, and real-time data streaming across physical servers. Understanding this structural evolution is the only way an architect can accurately evaluate MongoDB for a high-throughput, production-grade workload. This 3D model reveals the internal architecture of a single MongoDB server. It relies on two primary components: the wired Tiger storage cache, which manages active memory, and the operations log, or OPLOG, which acts as the ledger. When a standard write operation hits this primary node, the data enters the cache. But before the system returns a success signal to the client application, it writes a permanent line item to the OPLOG. The OPLOG is an idempotent, append-only log. It sequentially records every single state change that occurs in the database, step by step. You can scale this single node vertically by adding RAM and CPU, but eventually you hit a hard physical limit. Worse, this single server represents a single point of failure. To guarantee system redundancy, we deploy a replica set. The single server becomes a primary node, backed by two identical secondary nodes, forming a network. A common misconception is that these secondary nodes process raw queries directly from the client application to stay updated. They do not. Instead, the secondaries continuously pull and replicate the OPLOG entries from the primary node. They apply those identical state changes to their own storage cache. This synchronization allows developers to configure specific write concerns, primarily a setting known as W majority. With W majority enabled, the primary node receives a write and pauses. It waits for an acknowledgement that the write has been successfully copied to at least one secondary's OPLOG before confirming the write back to the client application. If the primary node crashes unexpectedly, an automatic failover occurs. Because the secondary already acknowledged the OPLOG entry, the system promotes it to the new primary without losing confirmed data or causing a catastrophic data rollback. High availability does not rely on hardware stability. It depends entirely on the OPLOG acting as a synchronized, distributed ledger of truth across multiple machines. Looking at the performance meters on this replica set, we see a limitation. Even with high availability secured, throughput is capped by the physical CPU and RAM of these servers. Sharding bypasses those limitations. We scale out horizontally by deploying multiple replica sets side by side. To manage this expanded infrastructure, we introduce the Mongoose query router. This acts as a protective abstraction layer. The client application talks only to the router, unaware that its data is split across multiple physical shards below. The router itself stores no application data. To know where specific records live, it queries a dedicated cluster called the config servers, which hold the metadata map for the entire system. As massive collections grow, the system initiates chunk splitting. The data is mathematically divided into default 64 megabyte pieces and distributed across the available shards to balance the storage load. This entire routing system relies on a single architectural decision made by the developer, the selection of the shard key. The first routing algorithm is hashed sharding. The router applies a mathematical hash to the shard key, which scatters the data wildly but evenly across all shards. This guarantees perfect write distribution and prevents localized server hotspots. The second algorithm is ranged sharding. Sequential data is kept together on specific shards based on alphabetical or numerical ranges. This enables highly efficient targeted queries, where related data must be read together without scanning the entire cluster. If a shard key lacks cardinality, meaning too many documents share the exact same key value, the system creates jumbo chunks. These are massive, indivisible blocks of data that the internal balancer cannot move, crippling the cluster's performance. Horizontal scaling requires strict mathematical routing. The shard key dictates whether a cluster scales efficiently or collapses under its own weight. Once data is horizontally scaled, a new challenge arises. How do you query a single dataset that is fractured across multiple independent physical servers? This animation demonstrates how MongoDB handles this using the aggregation pipeline. When a distributed query runs, the system pushes the .match filtering stage down to the local shards first. It filters out the irrelevant data at the source, drastically reducing network traffic. Only the surviving data flows up to the Mongoose router. There, a .group stage mathematically merges the disparate streams into a single condensed output for the client. This distributed model brings us to the most frequent criticism of NoSQL databases, the historical lack of strict relational-style AC transactions. Starting in version 4.2, MongoDB solved this by introducing distributed, multi-document transactions using a two-phase commit protocol across the shards. During a transaction, the system enforces snapshot isolation. No queries can see the in-progress state until all shards are ready to finalize it. The config servers manage the coordination phase. They ensure an all-or-nothing outcome. Either both shards write the data permanently, or both abort the operation entirely. This capability bridges a massive architectural gap. It maintains the speed of a document model while providing the rigorous guarantees required by relational workloads. We now have a fully constructed, production-ready architecture, client applications routing through Mongoose, config servers mapping the network, and highly available sharded replica sets storing the data. Implementing real-time streaming requires returning to the foundational component we first examined, the oplog. Modern event-driven architectures cannot rely on constantly polling a database to check for new data. The database must proactively push real-time updates outward to the rest of the system. This data flow visualizes how MongoDB executes this via change streams. This API physically tethers directly to the oplog. Whenever an update occurs, the ledger entry instantly triggers a secondary pathway, streaming the exact state change outward to message brokers like Apache Kafka. The fault tolerance mechanism for this streaming architecture relies on resume tokens. If a network connection drops, the downstream service holds a resume token. Because the oplog is a deterministic sequential ledger, the service presents the token to pick up the data stream exactly where it left off, without missing a single event. We started with a single document server. By relying on append-only logs and mathematical routing, that node scales into a global, event-driven data mesh. MongoDB's evolution is defined by leveraging these foundational mechanics to master distributed systems, retiring its reputation as a simple prototyping tool and establishing itself as a standard for